let's start. Go over that example again that I miscopied last time. We'll do a few more examples here and then move on to the next topic. So it was a -3, not a +3 that I meant to copy. Okay, so how would we have done that?
You can either divide it or add and subtract different values of 1 to make it cancel.
Okay. So what would that look like here?
Like, you do 4x squared minus 3x and then minus.
Well, I put -4x minus 3.
Yeah, and then you have to do plus
Right.
x, right?
And then I would have to actually have a -3x, I give myself a -4x, then what would happen?
Plus x.
I have to add an x, so I didn't change the top. And here I have a +2, and to get to a -3 from a +2, what do I need to do? I need to add a 5. And I can split these up into 2 fractions now, like this one and this one. So this is really the integral of 1 plus x plus 5 over 4x squared plus 4x plus. And so now this guy will actually factor, which was the whole point of this, to know that we can apply partial fractions here. That was 2x and 3, 2x and 1. If I made it a -6x plus 2x, that would have done it. So here, I know I'm going to split this into partial fractions, where this is 2x minus 3 and 2x plus 1. What's the quickest way to get the numbers here?
And what equals like the other, or is that 1 equal to 0? So 2x minus 3.
So 2x minus 3 equals 0. This means that my x would be 3 over 2. So I'm going to go over here, ignore that part, and plug in x equals 3 over 2. So the numerator here is going to be 3 over 2 plus 5 divided by 2 times 3 over 2 plus 1. That's going to be the number over there. Plus, figure out what makes this 0. It's x equals minus a half. So I'm going to go over here, cover that up, and plug in minus a half for x everywhere. So that's going to give me minus a half plus 5 divided by 2 times minus a half minus 3. So this ends up being just the integral of 1 plus, so 3 over 2 plus 5 is what, 13 over 2? And then this cancels, that gives you 4, so that becomes 13 over 8. Here I have minus a half plus 5, that's 9 over 2. This cancels, that would give me minus 4, so that's minus 9 over 8. And that's our partial fractions. So the integral of this is x plus, this would be 13 over 8. What's the integral of 1 over 2x minus 3?
1/2 ln.
1/2 ln of 2x minus 3 minus 9 over 8 times 1/2 ln of 2x plus 1 plus c. So that's your answer. How about this one? Let's say you were given this integral. What would you do there? And this is like random now, like it's an open-ended question. Any technique you want to use, you can apply. Yeah.
Subtract 1 of the numerator and then like split the fraction. I think that's
But you can't really subtract 1. Right? You can subtract 1 and add 1, right? But if you just randomly subtract 1, you're changing the value.
okay.
Yeah?
Can you like split the numerator up and make it into two integrals so you can do the integral of x squared over x cubed plus 3x minus 4 and do a u sub for that one? And then the second one.
Oh, would a u sub help you there?
We
Because
just
you
need
did
to do
a.
ln. Actually, never mind.
Hmm?
Never mind.
And then for the second integral, you could like.
No, but if you're going to do a u sub, you do the bottom, right? Right, the derivative of that's going to have 2 terms in it. So probably splitting it so you have only 1 term is not the way to go. But let's say you tried that. What would we get here? What is the
3x squared plus 3.
do you see anything?
Yeah.
Yeah.
You could actually just factor out a 3. That's your x squared plus 1 dx right there. So this guy is actually, you didn't have to do partial fractions at all. So you just apply this, and it just becomes 1/3 times the integral of 1 over u du. So it ends up, it is an ln of this guy. Now, another thing that was also sort of a dead giveaway that you can't, or you wouldn't try to use partial fractions is look at the denominator. To be able to do partial fractions, you have to be able to factor the denominator. Could you actually factor x cubed plus 3x
No.
minus 4?
No.
I mean, well, you probably can, but I don't think it would be worth your while to do that. Right? It's usually, I mean, in this class, it's not usually going to be some sort of crazy factoring. I mean, using the rational roots theorem, you can probably figure out a factorization. Yeah.
What happened to the part that we have from 1 over x cubed plus 3x minus 1? Or did that get part, was that part of t?
Yeah, that's all the whole, this is x squared
Oh,
plus
okay.
1. The whole
Okay.
thing got replaced.
Okay.
Yeah. So if you see that on a random exam or in a test where you don't know really what section you're supposed to be looking at, again, you always sort of start with the easier things like substitution. Like this is the first thing you'll think of with any integral. And then if that doesn't work, then you try something a little bit more complicated. In this case, if you tried substitution, you wouldn't get something as useful. For one, your substitution will give you, if you do u equals the denominator, the substitution you'll have 2 terms, but you have 3 terms in the numerator, and so on and so forth. So u sub directly doesn't seem to work here. You could do a trig sub, but you probably want to avoid that. Well, no, with a cube, that's going to be also kind of tough.
Did you factor the top?
Yeah.
I don't know where that gets you, but.
Okay, you could factor the top, right? That would get you what?
X minus 2, x plus 1.
Now, can you factor the bottom? Do you guys remember how to factor something like the bottom? Which, by the way, you could sort of do that technique here, but the only thing why I avoided that here is because substitution would normally be the first one, I think, and here it just kind of worked out. Here it didn't. So at this point, I'm sort of out of options. Trig sub can't really work, a direct u sub can't really work. So now I'm going to think, can I actually factor that denominator? Do you remember how to check if you can factor a denominator? I don't remember if I mentioned it in this class. The rational roots theorem, did I mention that? Did I?
Yeah, like a little.
Okay. So yeah, the rational roots theorem, that's a thing, we could use that here. Notice that, again, you try the factors of the constants divided by the factors of the numerator, but in this case it's 1. So you start to think of, how can I break up the factors of 4? Well, it's 1 and 2 and 4. Right? And you start to try to plug in those x values. Clearly plugging in 1 plus or minus 1 is not going to work. Then I move on to 2. If I plug in 2, 2 would work. Right? If I plug in x equals 2, if I take 2 cubed minus 2 times 2 minus 4, that is actually 0. Right? You want to plug in an x value that gets you 0. So that would mean that x minus 2 is a factor of this guy. Which means you should be able to divide this guy by x minus 2, and you end up with something without a remainder. You just end up with a quotient. So then you can apply your long division. Let's divide this x cubed, x squared, minus 2x, minus 4. How would you do that division?
Times x squared.
X into x cubed goes x squared times this, x cubed. X squared times minus 2 is minus 2x squared. Subtract, those die. This becomes a 2x squared. And you repeat the process. X into 2x squared is plus 2x. 2x times this is 2x squared. 2x times minus 2 is minus 4x. Those would die. Here you have a minus 2x plus 4x, so that gives you 2x. X into 2x goes 2. And then you say 2 times this gives you 2x. 2 times this gives you minus 4. Subtract, those die. So you have minus 4 plus 4, so you get a 0. Which means you can factor this guy into this times that. So you could have done that. Now you can cancel that. And so now you end up with the integral of x plus 1 over x squared plus 2x plus 2. How do you deal with that one?
You could complete the square for x squared plus 2x. You could add 1 and then maybe
Just do
then
use up.
subtract 1 from the denominator. And so you'd have x plus 1 squared plus 1, and then try and split them up and do a u sub to get arctan of x.
Use x plus 1. That. I mean, that's one way to go, but I probably wouldn't go that far. Thinking too complicated. I've tried u sub again. If you did u sub equals this,
Oh, yeah.
Just goes to x plus 1.
then your du is 2x plus 2 dx, which is just 2 times x plus 1. So this guy really becomes 1/2 times 1 over u du. So we know that the answer is going to be 1/2 ln of u. So the moral of the story is pretty much the answer to the question, what would you try first, is always substitution. If it doesn't work out, you try something else, but it's usually going to be the first thing you want to look at. Because if it does work, it will be the easiest way to do something. Whereas, yeah, completing the square and getting x plus 1 all squared and doing, you can do it u equals x plus 1. You could get to an answer that way, but it probably wouldn't have been very nice. Because I think you're thinking of just doing x plus 1. This would be x plus 1 squared plus 1. This is actually true. I never thought if this would work out because I would have thought of this first and then I wouldn't even worry about that. But you could do something like, sure, u equals x plus 1 here, and then this integral would just become u over u squared plus 1 du. And how would you do with that? Then you'd end up doing a substitution again, right? You'll end up substituting eventually. So here I do, let's use another variable, t equals u squared plus 1. Your dt would be 2u du. So eventually you'll get to 1/2 over the integral of t dt. Brings you to 1/2 ln of t. And so that's 1/2 ln of u squared plus 1. But that's 1/2 ln of x plus 1 squared plus 1 plus c, which ends up being the same thing. So you could get there. You wouldn't really get an arctan here because of the top. It's not a constant.
Could you have, but you could have split the two, right? You could have made it x over x plus 1 and then had a plus 1 over u squared plus 1.
That is another option. But again, that's the more complicated way to think about it.
Yeah, that's how you get the arctan.
So you could have thought of that as x over x plus 1 squared plus 1 plus 1 over x plus 1 squared plus 1. And sure, this one would give you like a tan inverse of x plus 1. But how would you deal with that guy? I mean, again, you could actually deal with that with substitution. The easiest thing would be to do substitution, but if it seems you're trying your best to avoid substitution, if you're doing that, then this would force you into a trig sub, and that would be pretty annoying. So yeah, the moral of the story is you always try substitution first. If it works, it'll work. And yeah, you'll definitely encounter problems where you might have a knee-jerk reaction to do a certain thing, like maybe try partial fraction. Always try u sub first. When you're satisfied that that will not work, you try something else. Or you always try to, and yes, there's more than one way to skin a cat. Just always try to think of the simplest way to do it. Yeah, so we'll kind of end the section there. I think we've learned all we need to learn from the partial fractions chapter. But the moral here is that we're learning newer and more techniques about how to do integrals. So now, while this does give us the ability to do more complicated integrals, it also provides us with a choice overload. So now you have a choice of methods that you can choose to do something. And so a part of being proficient at this is being able to choose the right method to deal with the job that you need to deal with, and to deal with that in the most efficient way. And generally, the sort of rule of thumb is try to get away with the easiest technique first, right? So you don't want to ever, the first thought should be trig sub. That should never be what is your thought. You always thought, can I use the power rule? No. Can I use substitution? That's where you start. You always start here, and you try to manipulate things to be able to use simpler rules, and if that doesn't work, then you try to hit it with something more complicated. We're going to move on now to actually 7.7. There's a section on integration techniques. I guess I'll talk about that after we finish chapter 7, which is just, again, about how do you approach this random integral. You don't know what technique you should use. How should you look at it? What should you try first, second, third? So we'll talk about that after we do chapter 7. But now we're going to move on to 7.7. Let's pass these in. So back when I was covering this topic as a wee little lad in Calc 2, they force us to memorize all these formulas, but I think I'll give them to you. I don't really see any benefit. Like, looking back at my life, I was like, when did I ever find memorizing that formula useful? Never. So there's some things it's worth memorizing because it gives you some sort of mathematical maturity or some sort of pattern that you can recognize elsewhere. Like, oh, I can use this other thing over here. But yeah, I've never used this formula for anything else. I would assume not many people do. It's an important nonetheless, but it's the kind of thing, if you need to use it, you'll only ever use it in this one context, and then you just look it up. It's not something you go around having memorized. So it's called Approximate Integration. And as its name suggests, it's talking about us approximating integrals. And you might want to say, well, we have all these powerful techniques now. Why do we need to approximate anything? Just find the answer. Turns out, integration is a little bit more complicated than that. There are relatively simple functions for which there is no answer, technically speaking. If you consider things like, I mentioned these guys before, like integral of e to the x squared, for example. Seems like a very simple function. E to the x squared, I can find the derivative of that easily, no problem. But the integral is a completely different story. There actually is no integral. There's no general antiderivative for that function. There's no set of functions that you can write down that if you take its derivative, you get this as the answer, right? Similarly, I can talk about sine of x cubed. Good luck integrating that. It doesn't matter what technique you do, that's not going to have an answer. You will not be able to write a function down that when you differentiate it, sine of x cubed is the answer. It's not going to happen. Right? So there are little guys like this that sort of make things annoying, and so we can actually find an answer, but there are situations in which we can find a good enough answer, an approximation to the answer. So these have no general antiderivatives. Right? There are cases where these guys show up and they're very important to be considered, and so you'll call them something. So we'll call, this for example is called the elliptic integral, you might see in some cases. And they just put a symbol that represents that integral, but everyone knows, you can't really compute it, but it's there in the answer, so we just use it. It's kind of like when you got to a point where you had the square root of -1. At some point you needed to get an answer, oh, let's just call this I, and develop a whole new mathematical theory to have that set up in it, right? So yeah, eventually with some of these integrals, it gets to a point where knowing this integral is actually important. So you just call it a letter, and you just do your math with that letter in it, knowing that you can never actually make sense of it in the real world. But yeah, so there are things like that that show up in calculus, where all the integration techniques you can have in the world will not help you. So they can have no general antiderivatives, but in that case you go back to the fundamentals. You go back to the concept of the Riemann sum, how the integral even came about being. And in the definite integral case, you can come up with answers. So if you're given, hey, find the integral of e to the x squared dx, you give up on life. However, if you're told 0 to 1, now we're in business, we can do something. I don't know what the general integral of that is, but I can approximate pretty well, pretty much as accurately as I want to. You tell me a number of decimal places that you want me to be accurate to, and I can get it to that accuracy, right? Once you give me actually limits on these integrals, I can use all sorts of approximation methods. And that leads us to the topic of 7.7, the approximate integration. This is going to be where we learn several techniques to approximate definite integrals. So sometimes you cannot find a general antiderivative, i.e. you cannot compute an indefinite integral, but we always have options with definite integrals. In this class, we're going to cover a few of them. They're listed on that handout that I just gave you. So there are things like the right-hand rule. There's the left-hand rule. These first three are very similar. I'm going to show you what those guys are. There's the midpoint rule. You can get a little bit more sophisticated and you can talk about things like called the trapezoid rule and Simpson's rule. Now, the idea behind having all these techniques, and there are more, but these are the only ones we'll cover. So we'll cover these, but there are more ways to think of an integral and actually build it up from a sort of Riemann sums idea. And there are ideas besides Riemann sums for which you can develop an integral, but we'll talk about these particular techniques here. And the reason for all these different techniques is that you can get to better approximations depending on the kind of function you're using by choosing a more appropriate method. Or sometimes, if you want to like program a computer to do one of these methods, sometimes choosing one method would cause a longer computational time and a lot more computational baggage than choosing another method. So there is a sort of appropriateness by choosing one method over another, and that's where all these methods actually come from. So I can sort of illustrate to you what's going on here. Let's say we want to approximate the integral from, say, 1 to 5 of x squared plus 1. Let's say that's our goal. Right, so I'm going to describe to you what these three methods in their concept would look like. Suppose we use 4 subintervals. Okay. Here's sort of what they would look like. Luckily, at the level of Calc 2, being able to choose the appropriate one for the appropriate case is not something I expect you to know. I will literally ask you. I will say, use the trapezoid rule to approximate this. So I'm going to tell you which one I want you to use, right? Being able to choose, in this case, this would be better. It's something that you have to be sort of above this level and look back and sort of figure out. But I'm going to just generally describe the idea behind this. So we kind of know, let's say we're using the left hand. Here's what that situation would look like. So I know my x squared plus 1 is going to be a parabola that's going up like that. and I want to approximate the area under the curve between 1 and 5. So the idea when I tell you we're using 4 subintervals, what that means is I'm going to cut this interval into 4 equal pieces. And there are methods that don't require you to have equal sized pieces, but in our setup we're going to assume that we're cutting it into 4 equal pieces. In this case, they will each have length 1, 2, 3, 4, 5. And the idea is, on that interval, I will erect rectangles whose left side touches the curve. So you'll notice that for each interval, let's say the interval 1 to 2, I'm going to extend the left side of that interval to hit the curve, and I'm going to define that to be the top of my rectangle. And I do this for every subinterval. So from the 2 to 3, the left side goes up, hits the curve, that's the top of my rectangle. 3 to 4, the left side goes up, hits the curve, that's the top of my rectangle. 4 to 5, the left side goes up, hits the curve, that's the top of my rectangle. And so I will approximate the area under this curve by just adding up the area of these 4 rectangles that I just created. And you can notice in this case, by the way, we'll have an underestimate here, right? Because the area of my rectangles leaves out some of the areas. So this is a technique that I could have applied, but I would do it with the idea that I know whatever answer I get from this approximation will always be slightly smaller than the actual answer, right? So in the case of using the left-hand rule here, it will actually give me a smaller answer. However, if you're in a case where not having enough is detrimental and having more is not appropriate, but it will be better than not having enough, you might want to choose another rule. I don't know, let's say you're an engineer and you're in some sort of situation where this integral is helping you calculate how much weight a bridge can hold. You expect the amount of weight to be the area under this curve, and so you want to do some sort of approximation to choose how you're going to handle your materials. Having a bridge that is under how much weight that you'll expect to be is not a good idea. It's much better that your bridge can hold more weight than you expected. And so any technique where you're using this sort of technique is probably not the one you're going to want to use. Something like that. Right? We're not worried about the applications here. I just want you to know how to do it. But sometimes underestimates aren't good. So there's something like the right-hand rule. Now this is a very similar technique to the left-hand rule, except we choose the right side of our intervals to be. So again, let's say we're going between 1 and 5. This will split up into 4 equal sections at 2, 3, 4, 5. I want the right side to hit that, and that's going to define the height of my integral. The right side hits that defines it. The right side hits that defines it. The right side hits that defines it. And I can approximate the area under this curve by taking the area of all of these 4 integrals that I just created. Notice, this gives an underestimate. This gives an overestimate in this case, which should be emphasized. Like, the right-hand rule doesn't always give an overestimate. It gave one because this function is increasing. If my function was decreasing, it would give an underestimate. So it's another approximation. So you might want to come up with a scenario that, you know what, let's try to minimize the underestimation thing or the overestimation thing. And so you kind of develop a midpoint rule. Now in general, this one will converge to the answer faster than either the left or the right hand rule, because what it does, it allows you to give a little bit of overestimate and underestimate at the same time. And so you kind of expect these things to even out faster. What this guy would look like is I would have the interval from 1 to 5. I would cut it into 4 equal pieces, 2, 3, 4, 5. But now I'm going to define the midpoint of all these subintervals. That's the guy in the middle, so this would be 1.5, 2.5, 3.5, 4.5, and I will let the middle piece define the height of the rectangle. And so, if that's the height, that's what that guy's gonna look like. And if that's the height, it's gonna look like that. So you'll notice here that it underestimates on this side of the rectangle, but it tries to compensate for that by making an overestimate on that side of the rectangle. So you expect this to minimize under and overestimates. So in general, if you're programming these three methods into a computer, the computer that has the midpoint rule programmed into it will more than likely get to an answer faster with less computations using less subintervals than a program that has one of these two programmed into it. Right? So a lot of it is, all of these would get you to some answer, and the more rectangles you use, they'll all get better approximations, but it's a matter of sometimes of, in this particular situation, what gets me to the answer faster with less computation, with more ease. Right? So that's sort of the idea. Then you can do something like, so that's illustrating the left hand, the right hand, the midpoint. Dissect it into however any subintervals you need. In the left one, the height of the rectangles are defined by the left side of your subinterval. Here, the height is defined by the right side of your subinterval. Here, the height is determined by the midpoint of your subintervals. Then you can go to something like the trapezoid rule. And as its name suggests, you use trapezoids. So you might want something even better than that one in this case. And you might say, okay, instead of using rectangles, let's use trapezoids. So we have a function that's increasing. This is between 1 and 5. Split it up into 4 equal sections. But you know what? On this interval, I'm going to erect a trapezoid. So it's a rectangle with a slanted top. And I kind of slant it so that it kind of approximates the curve a little better. So I'm going to slant them all down. So trapezoid, applying the trapezoid rule here would look something like that. Instead of erecting rectangles, you're erecting a bunch of trapezoids. And you want to estimate the area of the curve by estimating the area of these trapezoids. And so of course you have to remember how to find the area of the trapezoids. It's half the sum of the two parallel sides times the distance between them. And you're going to see all these rules, like when we're doing them, it's going to make all these formulas make sense that I'm running out. Because when you're doing a bunch of error formulas here, and that's why these guys kind of work out the way they do. So again, it's about approximating areas if we can't integrate something. And you kind of do it by erected rectangles. The more rectangles you use, the better the approximation. Trapezoidal rule uses trapezoids. The Simpson's rule is a little bit more complicated. It's not going to be a nice illustration on this particular example, but that one uses parabolas. So that's when you want to get away from the straight line idea and you want to be able to follow the curve of a function better. So you use a parabola instead of a, So if you're looking at Simpson's rule, and this one, the formula for this one is not as straightforward because it uses polynomial interpolation, and you do that and you get a general formula and you kind of apply it. But these guys are very straightforward. You can derive these by hand, derive those formulas I gave you by hand, and it wouldn't actually be that difficult. This one is a little bit more difficult. But the idea is he uses parabolas. So if you have something like a curve doing its random thing like that, he'll break it up into intervals where on this side he's using an upside down parabola to approximate the area, whereas on this one he's using a lower parabola to approximate the area. So he's erecting a bunch of parabolas to kind of try to fit closer to the curve. right? I mean, for here, they probably won't look so nice, because this is already just one big parabola. We kind of forced us to use 4. Simpson's rule here would look something like this. You'll approximate this guy with a mini parabola here. You'd use a bigger parabola that will span 2 rectangles, and then the end one will span by another rectangle. So it's kind of trying to take the curvature of the function into account. And you find the area under these parabolas. You add them all up and you get Simpson's rule. By the way, this one requires Simpson's. It's the only one that has this sort of requirement. Simpson's rule requires that you use an even number of subintervals. Because to get the polynomial interpolation to work, you need a certain number of points. But that's sort of the idea. So these are 3 different ideas on how to approximate areas under a curve, particularly in cases where the actual function is something that you don't know how to integrate and get to the exact answer. So what you do is you can use rectangles or trapezoids or polynomials to approximate what that area should look like. And if the approximation isn't good enough, use more rectangles, use more trapezoid, use more parabolas. Eventually you start to close in the gaps even more. That's the idea. Like if I use more guys here, I would actually get a better estimate. Right? The more rectangles you use, the better you get. So you pretty much run a program until, so if you do it 1,000 times and you get a certain answer, and you do it 2,000 times, if the first few decimal places that you're comfortable with didn't change, it means 1,000 times is good enough. Right? But if the numbers are changing and you're not getting the accuracy that you want, you just extend it and you do more subintervals and you just compute it more times. Okay? In this class though, you don't have to worry about that. I will tell you, use this method, use this many subintervals, and you just do the computations and show me that you know how to do that. But this is basically the idea. Another thing, so we're not actually going to compute anything, I'm just sort of explaining to you the idea behind it. In the next class we'll start to actually use this and compute some answers. Errors are going to be important, right? Difference between our approximation and the actual answer is called the error. Right? That's a technical term, it's called the error. Approximation is called the error. And it turns out we can actually compute the error of each of these methods. That one takes a little bit higher calculus than we've currently looked at. I mean, after we look at series, we can do a little bit more. Yeah.
How do we have the actual answer to compare it to if, like, this is for functions that we can't find the actual answer for? Or is it just like the differences between?
Okay, so we'll get to that. Basically what I want to say about error is we can actually compute formulas. There are error formulas on the next page that tells you the error associated with each of these methods. So that actually tells you how good you can be. So you'll actually know how far away from the actual answer you are using these formulas. They're derived using techniques I haven't taught you guys yet, and I'm not sure if by the end of the semester I'll teach you the techniques for that. But you can prove how far away from the actual answer you are. Second of all, if you're doing this in the naive way, and I'll just end up with this, it's not really a part of the syllabus or the topic at hand. But let's say you're in the real world and you don't know really how to judge the error, and you're like, how do I know if I'm getting close to the answer or not? Right? It's a valid question. So let's say you use, I'm making up numbers here. So let's say you use n equals 50, right? You plug this into a computer and it gives you an answer, right? It gives you 1.2379, whatever. Then okay, let's up it to n equals 100. Then the computer outputs 1.3126. Then okay, n equals 150. Okay, it goes to 1.3174. Then you put n equals 500. You get all the 1.3175, blah, blah, blah. You'll realize that you are approaching an answer. But you'll notice that when you're upping the things, there's a certain amount of decimal places that will not change. So you can say, I'm at least sure of the first 3 decimal places. I'm accurate up to 1,000th of a unit, right? Because once you're increasing the approximation, that part isn't getting better. It's the other things that are changing. So even if you don't really know a formula ahead of time for how to compute your error, just by practice empirically, you'll be able to see it. Because the answer is, because you're actually doing a limit here. Remember, an integral is a limit. So you are approaching an answer. So even though you don't know what that answer is, you'll know when you're approaching it and when you're getting closer. Because a part of the answer will always be the same. And the part that you're not sure about will happen to be the part that keeps changing. But yeah, we'll actually compute these next time. Do an example where we're computing some of these. And we'll stop there. So the part, was the partial